Okay, so in this video we're going to continue our discussion about circuits. At the end of the last video we talked about the definition of electrical resistance, and we talked about Ohm's law, and the concept of how some materials at a constant temperature have a constant resistance, and that materials that obey that kind of relationship are what are called ohmic materials. Okay, so those are materials that have a constant resistance at a constant temperature. Okay, and so I had some people ask me what a resistor is, and this is basically what a resistor looks like. Here's 3 different resistors right here, and you can buy these really cheap to make basic circuits. Now, the circuit diagram symbol for a resistor for the IB is like a little rectangle. Okay, and so that's what you see right here. This is how you would draw a resistor in circuit diagram notation. The notation we're going to use is slightly different. I'm going to use a more conventional circuit diagram symbol for resistor when I'm drawing circuits, just because that's what I'm used to, and also a lot of the worksheets I have doesn't have the resistor drawn as a rectangle, it has it drawn as a squiggly, but we'll see that later. Okay, do you know, by the way, that this chart of circuit diagram symbols, this is given to you in the IB Data Booklet. I think it's towards the front, somewhere around the SI prefixes. Okay, so you don't need to like memorize all the different symbols for the different components. And so these are just normal resistors. These are built in such a way that they have a constant resistance. Some other types of resistors we'll talk about later are what's called an LDR, which is a light-dependent resistor. And basically the way it works is it can detect light intensity, and as the light intensity hitting the LDR increases, the resistance of the LDR decreases. Okay, and vice versa. When the light intensity decreases, that increases the resistance of the LDR. And so those can be used in interesting ways, and we'll talk about that at the end of this unit. And another type of resistor I want to mention is what's called a thermistor, which is kind of analogous to the LDR, except instead of working with light intensity, it works with temperature. Okay, and so a thermistor is a type of resistor whose resistance changes as a function of temperature. And so as you increase the temperature of the thermistor, it actually decreases the resistance. And as the temperature in the thermistor decreases, the resistance increases. And so those are 2 special types of resistors, and we'll talk about those later. Those are used in different types of sensor circuits to set off different types of circuits. One example that we'll talk more about later is, for example, you might see a thermistor in a circuit designed to set off like a sprinkler system. If there's a fire, then you could build a circuit with a thermistor, and so if there's a fire and the temperature in the room increases too much, then it knows to set off the sprinkler alarm or something like that. Okay, and so we'll talk more about that at the end of this unit. One thing I want to mention before we talk about power dissipation is calculating the voltage drop across a resistor. Okay, and so as current runs through a resistor, and when I say resistor here, I do mean the resistors that we just talked about, but more generically, I mean basically any device that's using power, any load attached to the circuit. Anytime you have a load hooked up to a circuit, there's going to be a voltage drop across that load. In other words, one end of the load has a higher potential than the other side. Okay, and so this is what we call a voltage drop or a potential drop, and we'll talk about this a lot. And we kind of saw like a little animation a while back with like a little kind of conveyor belt system. Let me see if I can find it. Something like this. And so when we talk about a voltage drop, we know a voltage source like a battery is used to lift charge up to a higher potential, but when that charge goes back around, that potential gets used up, and that energy gets used up inside the load. And so that's what we refer to as a potential drop or a voltage drop. There's literally a drop in voltage from one end of the load to the other load, or to the other end of the load. Okay, and so to calculate the value of that voltage drop is very simple. Okay, all you have to do is use the equation V equals I times R. Okay, and this equation works whether or not the device is ohmic or not. It makes no difference. If you know the current going through a component, and you know the resistance of that component, at least the resistance at that moment in time, then I times R gives you the voltage drop across that component. Okay, and so that equation gives you a really easy way to calculate voltage drop. Okay, all you have to know is the current and the resistance. And if the component is ohmic, then of course R is constant, but whether or not it's ohmic or not, the equation still works. Okay, I times R still gives you voltage. Okay, so keeping that in mind, we're going to take a brief detour and talk about power dissipation. Okay, and so that energy that's used up inside a component when there's a voltage drop, that energy goes into, among other things, it goes into heat. Okay, and so we can calculate the power used by a component, and I will do a simple derivation. You can see it here, but basically the way this derivation works is going back to IB Physics 1, we know that one definition of power is the rate at which work is done over time. Okay, but in 5.1 we also saw that work is done on a charge given by the equation Q times delta V, okay, where delta V is the potential difference that the charge moves across. Now, in the circuits unit, we drop the delta just by convention, so we write QV where the delta is implied. And so if we make that substitution into the power equation, then we get an equation that looks like this, QV over T. But if you look right here, charge over time is current. That's like the definition of current. Okay, and so through the simple derivation process, we can come up with an equation that allows us to calculate the power used by an electrical component. Okay, and this is going to be our PIV equation, P equals I times V. Okay, so P represents the energy per unit time, the number of joules per second delivered to or consumed by an electrical component. Okay, so as long as you know the current through the component and the voltage across that component, you can calculate how much power is used by that component. Okay, so P equals I times V, PIV. Now, P equals I times V, I'm going to erase this for a second, so write this down if you want to have this. Okay, so P equals I times V. For reasons I don't understand, the data booklet writes this as P equals V times I, which is the same mathematically, of course, but it doesn't spell PIV, which I like. Okay, so it's the same equation. But also, if you have P equals I times V, we know that a voltage drop is given by V equals I times R. And so by making the appropriate substitutions into this equation, we can actually come up with two other equations for power. Okay, so for example, if I plug into V I times R, then that would give me P equals I times R, which would be I squared times R. And I could also make the same substitution, replacing I in this equation, and that would give me P equals V squared over R. And so there's actually three equations for power, and they're all three given in the IB data booklet, so you don't need to memorize them or anything. Which one you use, of course, just depends on what you're given in the problem. Okay, so obviously if you're given current and voltage, you would use the one that has current and voltage. And so we know what all the symbols represent. Power, I want to remind you, is measured in watts. Okay, that is a measure of how much or how quickly energy is being delivered or consumed by a component, and 1 watt is basically 1 joule per second. Okay, so it's a rate of how quickly energy is being used up per second. Okay, so we have three equations for power, and again, which one we use just depends on what's given. Okay, so let me give you a simple example. Pause it here if you need to add these equations to your notes. Okay, so example 1 says a 100 watt light bulb has a voltage of 12 volts placed across it. Okay, so 100 watt light bulb, that is the power used by the light bulb. Okay, that light bulb is using 100 joules per second. Okay, 100 watts. And so given a voltage, given a potential difference of 12 volts, we can find the current passing through the light bulb, which is I, just using our PIV equation. Okay, so I would look at my equations. I would say, okay, which one has P and V? Well, that would be P equals I times V. Oops, equals I times V. And so that would be 100 equals I times 12. And so I would be 100 divided by 12, which I'll just put that into the calculator. 100 divided by 12 is approximately 8.3 amperes. Now the second part of this question is asking what is the resistance of the light bulb? Now at this point I have more than enough information to answer the question. Either I could use another power equation, just use one that has resistance, or I could just go back to using V equals IR at this point. Okay, and either way is fine. I think probably just for simplicity I'm going to use the equation P equals V squared over R. Okay, just because I think I can do this one without a calculator. So if I want to find the resistance of the light bulb, I know P is 100. I know V is 12. And so to find the resistance, I'll do it here. I would do 12 squared divided by 100. That's 144 divided by 100, which is 1.44 ohms. Okay, so just a really simple calculation example with power in the context of circuits. Okay, so pause it there if you need to look at that some more. Okay, so let's take a look at one more example. This question says a blender runs on 5 amps, so that would be 5 amperes of current on 120 volts. How much power is the blender drawing? Okay, so see if you can answer that question on your own. Okay, so amperes, that's current, so that's I. We have the voltage here. So this is just a real basic type of calculation. Okay, so that would just be 5 times 120, which would be 600 watts. Now, if you look at up here, it says how much does it cost to use the blender. So 600 watts is 0.6 kilowatts. And the reason I bring that up is because when you are a grown-up and when you're paying for electricity or when you're going to find an electricity provider, the cost for electricity is usually given in terms of some number of cents per kilowatt hour. Okay, and usually it's somewhere between like 5 to 10 cents per kilowatt hour. So when you go to get your first apartment or you buy your first house, you have to find somebody to give you electricity. And usually the number you're looking at is so many cents per kilowatt hour. If it's more than 10 cents per kilowatt hour, then I don't know, that's kind of pricey. I definitely wouldn't go past like 15 or so. But of course, it also depends on where you live because some places have like monopolies on the electricity. And so you're paying per kilowatt hour. So in other words, if I run this blender that's 0.6 kilowatts, that's 600 joules per second. If I run that for 1 hour, that might cost me 10 cents. Okay, and that doesn't sound like a lot of money, and it's not. But if you have a bunch of other appliances in your house, like your TV, your computers, charging your phones, running your blender, etc., all that adds up over time. Okay, so just something to keep in mind as you're transitioning to adulthood. You're paying so many cents per kilowatt hour. All right, so moving on. And in case you're wondering, by the way, how much power different devices use, this is just like a simple chart that has some common appliances on it. You can see, blender somewhere in the 300 to 1,000 watt range. Microwave oven might be more. TVs nowadays tend to be pretty energy efficient, but still, if you leave on your TV all the time, then that uses up a lot of electricity. Okay, so for example, if you keep your plasma TV on 24/7, let's say for 24 hours, then that would be 0.24 kilowatts, and it's kilowatts because 240 watts is 0.24 kilowatts. And so if you leave that on for 24 hours, Let's see, that would be, I can't type numbers into a calculator. Okay, that would be 5.76 kilowatt hours. And so if you leave your TV on 1 day straight, then that might cost you, I don't know, 40 or 50 cents, which again, doesn't sound like a lot, and it's not, but if you do that every single day over the course of a month, that adds up. All right, so let's move on. In the circuits unit, power calculations tend to be pretty straightforward and simple. Okay, so I want to talk about circuit diagrams really quickly, and then we're going to get into a more complicated part of this unit. Okay, again, a full list of circuit symbols it's in your IB textbook, and it's also given to you in the data booklet towards the front. I just want to point out 4 basic circuit components and how we're going to look at that as we're drawing circuit diagrams. A lot of the components that you see in the data booklet you don't actually see in IB Physics SL because a lot of them are in HL. I will try to point out to you which components you definitely need to know about though. Okay, and keep in mind as we're drawing these components as circuit diagrams, we draw them connected via conducting wires, and to draw a conducting wire, you just draw a line, as we'll see. Okay, so these are the most common circuit diagram symbols that you need to be aware of. Okay, so first of all, and if you want to pause here and add this to your notes, that's fine. Okay, so first of all, you might have this individual battery, which is called a cell. Okay, and so that's drawn just like this. You got 2 lines. One line is longer, one line is shorter. Okay, the longer line is the positive side of the cell. Okay, in other words, it's the side of the cell that has a higher potential difference than the other side. Okay, so longer means more potential, shorter means less potential. So there's a potential difference between the long end and the short end. Okay, if you have a collection of cells together, that's what they call a battery. That's usually drawn like this. Okay, and just because it's more complicated to draw, usually I'll just draw cells because it's easier for me to draw. But yeah, that would just be like a collection of batteries. If you think about when you use batteries, a lot of the time you're not just using one individual battery, you're putting them together to kind of add their voltages together. Okay, by the way, if you look at like a AA battery, it'll say the voltage on that is about 1.5 volts, just to give you an idea. Another key component that you'll see all the time is what's called a switch. Okay, if we were in person, I would show you, we have some switches in my classroom. This is a very basic switch. Okay, a nicer looking one would be like a light switch or something like that. But basically a switch physically can break open the circuit, because if you don't have a closed conducting path, you can't have a circuit, because then the charge has no place to go. Okay, and so a switch like physically opens up or closes the circuit, and so when the switch is open, the current stops flowing. Okay, when the switch is closed, then you have a closed conducting path, and the current can flow again. Okay, which is pretty common sense. Most people are familiar with the concept of like a light switch or something like that. Okay, and then what we have a resistor. I am going to draw it with this little squiggly line because in this country, that's how we draw resistors. So if you ever take physics in college, this is how they will draw resistors. This is the IB notation, and that's probably how they do it in Europe or something. But since I'm not used to that, that's not how I'm going to draw the circuits. But just kind of keep that in mind, that difference. And we know what a resistor is because we already talked about those. Okay, so this is the chart that's in your IB data booklet, and we'll talk about some of these as we go along in this unit. Obviously, some of them, you know what they are, like, you know what a cell is, a battery, a switch is usually drawn as this open line right here, just so you can see it. Some of these we'll talk about later, and some of them we won't talk about at all. Okay, we're not going to talk about like diodes or capacitors or anything crazy like that. Okay, so here is a very basic circuit diagram. Okay, this is one of the most basic circuit diagrams you can have. So if you look at the circuit diagram at the bottom, we have a cell. Okay, it says it's a battery, but it's really just a cell because there's only one series of lines. Okay, you see the positive side, the positive terminal of the battery is on the right side. We know that because it's longer. And the shorter side is the negative side. Okay, now the way this works is current is always going to flow from high potential to low potential. Remember that the direction of current is the direction that positive charge flows in a circuit. So that means what's going to happen is the current is going to start here, and it's going to be driven down to a lower potential. And so the current is going to flow, in this case, counterclockwise. Okay, from plus to minus. Okay, so as long as the switch is closed, the current is going to flow counterclockwise. If the switch was open, then there would be no current because there's no conducting path. Okay, so that's what a very simple circuit diagram looks like. Okay, you can see the resistor there drawn as a squiggly, not in the IB notation style, but still that's how I'm going to draw them. And you can see the switch is drawn open like so. Okay, you almost always draw a switch being open because if you drew a switch closed, it would just be a line and then it would look like a wire. Okay, so usually when you're drawing a switch in a circuit diagram, you draw it as open so it's obvious that it's a switch. Okay, so pause there if you need to look at that some more. Okay, the last thing we're going to start off talking about is Kirchoffs Laws. Okay, now please make sure you take really good notes over the next few minutes. Kirchoff's circuit laws are basically like Newton's laws of motion. Okay, they are essential to solving problems or circuits. Okay, and there's two laws. One of them is pretty straightforward and the other is more complicated. Okay, and so I want you to go ahead and take notes over the laws in this video, and then over the next few days we'll get more and more in depth with solving problems with Kirchoff's laws. Okay, so here are Kirchoff's circuit laws. Okay, go ahead and pause it here and add this to your notes. Okay, so there's two of Kirchoff's circuit laws, and these laws are vital to being able to analyze circuits. Law number one is called the junction rule. Okay, and the junction rule is very intuitive and it makes complete sense. But basically it says that all the current flowing into a junction must flow out of that junction. Okay, so what does that mean, junction? That a junction is basically like a point where two wires connect together. Okay, so if you imagine like going back to the pipe analogy, if you imagine like two pipes coming together and forming a bigger pipe, the place where they meet up and combine together, that is a junction. Okay, so a junction is just a point where wires meet up together. Okay, and so according to Kirchoff's first law, the junction law, all the current going into a junction must flow out of the junction. And that is just because of conservation of charge, which we've talked about conservation of charge before. Because let's say Kirchoff's first law was not true. In order for this law to not be true, that means either current is going in and then just disappearing, or otherwise you have more current coming out than you have going in, which means you're magically creating like charge inside of that junction. And both of those violate the conservation of charge, which is one of the fundamental laws of the universe. Okay, and so the junction law, the junction rule or the junction law is just really a restatement of conservation of charge. Okay, that one is pretty intuitive. Most people don't have any issues understanding that. Kirchoff's second law is the loop rule. And this is the more important of the two. You could argue this is like the equivalent of Newton's second law in mechanics. It's that important. We'll be using it to solve lots of different types of problems. Okay, so the loop rule says this. The sum of the voltages, okay, so that's the sum of the potential differences, around any closed loop in a circuit must be 0. The sum of the voltages around any closed loop in a circuit must be 0. In other words, if you add up all the voltages around a closed loop, they must add to be 0. Okay, and we'll spend some time talking about that later, what that means conceptually. But basically, the loop rule is a conservation of energy statement. Okay, it's saying that basically in any given circuit, if you're going around the circuit, some places you go up in potential and some places you go down in potential. We saw that in the simple animation that we saw earlier. What the loop rule is saying is that if you go all the way around, everywhere you went up in potential, you had to go back down in potential by the same amount at some point. Okay, and so going back to that animation that we've seen a few times before. Okay, this is a really basic animation, a really basic circuit because there's only one component, but the principle is the same. Okay, the loop rule basically says if you pick any point along this circuit and you make a path going all the way around, by the time you come back to where you started, any place you went down in potential had to be balanced out by a place you went up in potential. Okay, so for example, if I start right here, if I go up this many volts, by the time I get down, or by the time I get back down to where I started, I had to go back down by the same number of volts. Okay, and so again, the loop rule is just a statement of conservation of energy. It's true for this really simple circuit, but it's also true for the most complicated circuit you can think of. Loop rule has to be true because energy has to be conserved. I guess it would be more accurate to say in all of the problems we're going to see at this level of physics, the loop rule has to be true. Okay, and so by combining these two laws, Kirchoff's two laws, that enables us to what we say simplify and solve a circuit. And when I say solve a circuit, basically that means we know the current, the resistance, and the voltage, and sometimes the power across the entire circuit. Okay, and so that's what we'll see over the next few days as we look at more and more complicated circuits and how to simplify those down using Kirchoff's laws. Okay, and so just to summarize, these three things are basically the keys to solving all circuit problems for the most part. Okay, so you have Ohm's law. Okay, V equals I times R. Here it's written as R equals V times I, which is just like the definition of resistance. But of course, we talked earlier in the video about V equals I times R. That's how you calculate the voltage drop across the component. And that in combination with both of Kirchoff's laws, both the loop rule and the junction rule, allow you to do basically anything you want with regard to circuits. Okay, and so in the next video or the next 2 or 3 videos, we're going to look at increasingly complicated situations involving circuits, how to simplify those down, and how to find unknown quantities using a combination of these circuit laws. Okay, and I'm just going to warn you now, it can get kind of dicey, but as long as you understand the concepts involved, especially with Kirchoff's laws, then it's really not that bad as long as you get some practice. Okay, so pause it here. Make sure you have all this into your notes. The very last thing I want to leave you with is you might be wondering what the heck is a loop, and so let me explain what a loop is before we end this video. Okay, and so the loop rule refers to if you make any closed loop, then the sum of all the voltages has to add to be 0. So what does that mean, a closed loop? Okay, when I say a closed loop, basically that means you can put your pen down somewhere in the circuit and start drawing a line without picking your pen up, and at some point, if you make it back to where you started without picking your pen up, that is a closed loop. It doesn't matter which path you took. It doesn't matter, which way you went, clockwise, counterclockwise. It doesn't matter. Okay, a closed loop is something you can draw on any circuit diagram. Doesn't matter how complicated the circuit diagram is, by putting your pen down at one point and then having your pen end up at the same point by going around somewhere. Okay, ending up back where you started. And Kirchoff's loop rule basically applies for any closed loop. Doesn't matter what it looks like, doesn't matter the direction, as long as you end up back where you started. Okay, the loop rule says that by the time you get back to where you started, all the voltages, all of the changes in potential that you went across all have to add to be 0. And so obviously some of those voltages might be positive, some of them might be negative, but we will really get into that more in the next video when we start doing problems involving Kirchoffs laws, calculation problems involving Kirchoffs laws. Okay, so I'm going to stop this video here. As always, please let me know if you have any questions, and I'll see you guys in the next video.